Yeah. Thank you also for the wonderful opportunity to present on what is honestly one of my most favorite parts about LLMs and one of the most exciting technologies I think that's coming out using LLMs. This is kind of creating a framework to apply LLMs at like a larger scale. It's not necessarily replacing like the underlying architecture. Although this is, I think, what would allow people to actually use it in real applications because it kind of broadens the abilities of LLMs quite a bit. So yeah, let's go into an overview of LLM agents. I kind of wanted to get started with this presentation by kind of looking at like the Peter Norvig and Stuart Russell definition of what an agent is, because I think it's a pretty good lens as to um, a pretty good lens to kind of like analyze like what are LLM agents kind of in the context of this definition of an agent and um, yeah and then also kind of like how do computer scientists and like people who do like game theory and stuff like that look at agents more generally. um, so an agent is defined here as anything that can be viewed as perceiving its environment through sensors and acting upon that environment through actuators. And then they also define an agent as both an architecture and a program, where in introduction, or like, yeah, artificial intelligence, a modern approach, they define architecture to be like the way that the agent interacts with the world. So how does it access its actuators? Um, as well as a program, which is kind of what the next little subpoint here talks about, which is like an agent action or agent program or agent function is like the algorithm which decides what actions to take next based off of the current set of presets, which is like, what is my current state that I observe and like what are all the previous states that I've observed previously. The agent function in and of itself is kind of like the current like state of like the function that you might run, whereas like the program kind of defines like the collective actions of like all the functions that are there. This is kind of like a subtle difference, which kind of is a little bit more important when you talk about like, oh, how do I define Bellman functions and stuff like that. But for LLM agents, this is actually not that important because like if we really think about like what LLMs are, we're not training them real time on the data that we see, right? Like we might be changing the prompts which we're passing into the LLM whenever we like use LLM agents, but the LLM itself is not being trained on the data that we are interacting with. So in this case, the agent function, like the underlying LLM, which is making the decisions, is like more or less the same every single time. So yeah, I think it's interesting, like when you like listen to the rest of this presentation, I think some of these definitions can be kind of like interesting to think about. Like what would like an LLM agent look like if the LLM were learning at the same time? Or if we were able to learn like specific prompts that we send into the LLM, which I think is kind of what some of like the current research is kind of heading towards, is like, how do I kind of optimize based off of like my use case or based off of like the previous information that I've seen to make better prompts and then also to make better like agentic frameworks and stuff like that. So yeah, so the two other definitions that I kind of wanted to bring up, which is, yeah, again, somewhat important towards understanding like the reasoning aspect of LLM agents, are goal-based agents and utility-based agents, which are two definitions which are actually kind of interlinked. So a goal-based agent basically looks at a particular goal state and then uses like the current its current understanding of the world around it to choose which actions to take to get to that goal state. But it doesn't necessarily differentiate between different states which are not the goal state. So it'll kind of like minimize its distance to get somewhere, but it doesn't necessarily like try to understand, is this goal state suboptimal for like reasons that don't have to do with the distance. So like if you're playing a game of Pac-Man, this might be kind of like the winning goal state might be to eat like all of like the like little balls on the screen. So that might be the winning goal state, and it's just gonna like take any path to like eat all of the balls, but it's not necessarily gonna try to optimize on like, how do I get all of the balls in like one single run? How do I avoid the ghosts and everything like that? Whereas utility-based agents will create what are called heuristics to kind of estimate like hey, what is the smartest way for me to get to like my intended goal? Like, what is actually the smartest move that I should make in any given point of time? And it doesn't even necessarily have to keep the end goal in mind. It's only going to kind of like try to optimize like on whatever actions it currently has. So like the most intelligent agents are kind of a mix between goal-based agents and utility-based agents because they'll both think about what's the smartest move that I should do right now, and then also what does my long-term strategy look like in order to get to the final goal state that I want to see. Um, so yeah, some of like the papers which have to do with the way that LLMs break down tasks and break down subtasks and do planning and stuff like that, do try to integrate like some of these ideas around not just can I make the most like the smartest statement, smartest, most accurate statement right now? Can I actually plan to make a statement that like gives me the most range in terms of what future steps I can then take to like solve whatever task I have to hand? And again, this is an open field of research. This is all very, very new. So like, I think it's also interesting from a, like, if you wanted to go try something out, like for yourself, like there's actually plenty of room to kind of go experiment with this. So yeah. So now that we have a better...
Sorry, would you take questions now or in the end?
Oh yeah, yeah. Actually, this might be a good place for people to ask questions because I know that this is a little bit more kind of a dense topic, I guess.
So how would you characterize the AlphaZero or Deep Blue? Is it a mix of utility plus goal based, or they are chess agents or whatever chess expert system? Yeah.
I think they actually are a mix of the two because I do believe that they explore different states and then try to create like a heuristic based off of the states that are there. To my understanding, like AlphaGo and like Deep Blue, like both of them explore. So like the way that they go about it is that they have like the goal of winning a game, but they don't just win the game. They explore as much of like the state space as possible. And like in game theory, the state space is kind of like any current given configuration of like objects which are on the board. Or actually like more generally speaking, it's like any given state that like you can be in while you're still playing the game. And in some cases, they'll even try to, I know that they try to run these experiments with like impossible game states as well to try to like optimize on like out of distribution tasks. So like what happens if I like have like, I initialize like a chessboard which actually like can't exist like in chess, it still might be helpful for like the model to internalize like the most optimal, like the most optimal set of actions, like in that case, the most optimal policy. Yeah, I don't know if that answered your question. That might have just introduced like more vocab.
No, it's definitely helps food for thought. Yeah, thank you.
Yeah,
hey,
that's
I had
actually...
a question.
Oh, go
Sorry,
ahead, Kurt.
No, I mean, I was just wondering, is this definition of agents that you have similar to the canonical definition of an agent in reinforcement learning? And is this goal-based agent and utility-based agent again sort of similar, if not exactly same as like model-based RL and model-free RL kind of distinctions?
So essentially, utility-based agents are like the general term for like RL agents. Because utility, like the utility that is being learned in like reinforcement learning is like the utility function that the utility-based agents make their decisions off of. And there are like tons and tons and tons of like ways in which to optimize on different like how, yeah, so the goal is kind of like the optimal endpoint that you're trying to optimize for. But like if you're thinking about this in terms of like I want to do reinforcement learning to make an agent that's really good at solving a problem, I'm not necessarily just going to tell the agent always go for the goal because that's not necessarily the best way to go about it. Actually, what you'll try to do instead is like create secondary objective functions that you then will minimize for. And those objective functions can be like any number of things. The Bellman equations that I mentioned earlier are like a really popular way of doing this, but it's not the only way.
I see. I see. So you're saying utility here is sort of the proxy for like a agent policy that is typically used in the RL literature, and goal is sort of a more coarse-grained utility, whether you reach the goal or not, versus utility could be far more elaborate.
No, so you would be reinforcement learning for the utility. So understanding what the utility should be. But the policy is actually the same as the agent program. policy and program are actually one and the same. It's just that policy tends to be used in like statistics textbooks more, and then like agent program tends to be used in like computer science textbooks.
I see. So utility is just a reward or
yeah, utility is the
okay.
reward function.
Okay, got it. Thank you.
Yeah. Sorry. Yeah. Any other questions on this in particular?
No, I'm really liking how the discussion is going. I know it is taking a little bit off track, but if let's say I want to book a travel to Iceland, let's say, and of course I want to minimize my cost, but also I want to get that done for a particular time period. But also I want to make sure the layovers and the travel and all of that is taken care of. So in that case, the hotels and all that, in that case, again, it's a mix of utility plus goal-based, right?
Yeah, exactly. And I would also say that like utility-based agents work if you have like a function that you can actually maximize. But then like goal-based agents work if like there's kind of a very clear dichotomy or like a set of classes that you can like fall into like with a particular game state. So one example is like if I'm playing chess, like I can always see on the board whether I have more or less pieces than the other person. It might be a goal of mine to like always have more pieces than the other person. But then that would kind of cause me to very aggressively start taking pieces, even if it's suboptimal for like my overall strategy. Which is kind of why you want to have a mix of both. Like having goals is not bad. It's just you have to be smart about the goals and then also smart about setting like what the reward function should be.
Right. The strategies like Queen's Gambit and all that probably it will not be in terms of if you just see that if it's just pieces you are caring about, then the Queen's Gambit is probably not one of the policy.
Yeah, or sticking to your own example, right? If you want to book a flight to Iceland, so goal-based agents only can differentiate between like a goal state or not. You can take a cruise or a flight or any form of transportation, whether like for a given state, how much utility you can derive, whether how much it is aligned to your goal. That like because a goal-based agent only can differentiate between whether a given state is goal or non-goal, right? But how much desirable utility you derive out of the state, that's where the utility-based agents come in.
Yeah, and so this is kind of where things get a little bit complicated with LLM agents because they don't have like very explicitly defined like reward functions, for example. Like LLM agents just generate information, but then they use that generated information to start making decisions. So in some ways, they're like a goal-based agent that makes like tons and tons and tons of like sub-goals. But then that kind of raises like this area of opportunity of like, what if I were able to make like a reward function like with like an LLM agent? I don't know what that would look like, but I would assume that would maybe be like I'm trying to calculate like the vector distance between like some output that I have and like so like if I were to encode like an output from an LLM, you might want to look at that as being like what is like the distance between that vector that I output and then like a vector that I'm really interested in like adhering to. So yeah.
I guess you're going to talk a little bit more on that line, right?
Yeah.
So basically how you can steer it based on the number of steps or the number of actions the LLM is deciding based on whether it's a goal-based or utility-based.
Exactly. And like 3 slides we'll be talking a little bit more about
so
this. But I actually think that this conversation is really good because like I don't have all the answers here and I do think that this would be a really interesting discussion once we're finished.
Thank you.
So yeah. So what are agents? And then now what are LLM agents? So generally, like this is kind of the definition that I found like on a few different blogs and stuff like that. One of them is like a guide to prompting, which is like a website, I guess. And then there's also a guide from like the NVIDIA developer blog, which basically says the exact same thing. An LLM agent is a system which can execute complex tasks using a structured prompting system, which recursively calls an underlying LLM instance. So as I said earlier, like an LLM doesn't necessarily learn from the information that is being passed into it unless you're explicitly fine-tuning it. Like it is like a state agnostic system. But then when we make agents, we actually do want them to have an idea of what the current state is. So like, how do we make like a stateful LLM? That's like one of the big goals of making LLM agents to begin with. And then more than that, if I'm trying to like execute on complex tasks, sorry about oh, I guess it's not. Okay, great. Sorry, there's like a notification that
like a full screen.
Oh. I think it's full screen on the actual thing. It's just not full screen on the thing in here.
That's okay.
I can do that for
Yeah.
everybody who's in the room.
Yeah.
I was just fixing one of the presentation things that's happening here. So yeah, one of the main goals with an LLM agent is like, how do I make a stateful LLM? And the other thing is that like there are a lot of limitations in terms of what you can prompt an LLM to actually do. And so kind of like all the things that exist is like the apparatus around like creating an agent, like this planning, the memory, the tools, like they're all basically like trying to cover up for the fact that the LLM is not really good at doing specific tasks. So you need to be using tools. That the context length is extremely limited in many of the smaller LLMs. So you have to find a way to extend your memory. And you might also want to have access to real-time data that you don't necessarily have fine-tuned into the LLM. And the other thing is that the planning in and of itself is not easy to do in a single step. So like you have all these examples of like few shot prompting, but few shots may not be enough, depending on the complexity of the LLM, depending on the complexity of the task, depending on like many different factors, which are kind of difficult to predict ahead of time. Like to an LLM, some questions may look very similar, but to like a person, we may understand that like a question, for example, that might seem similar on this, like simple on the surface is like, what is the meaning of life? But obviously everybody in this room knows that it's practically intractable to like try to figure out what the meaning of life is. But an LLM would not know to begin with. Like it would just take it and then it'd start like generating stuff. And in that case, like you wouldn't want the LLM to just be giving you the first thing that it generated. You'd want it to kind of like break down the question into sub pieces and then start thinking about, actually, do any of these sub pieces apply to this issue? Like, is this the optimal way to solve this problem? Like, can I even solve it in a certain given point of time? And that's where a lot of like the agentic stuff that we were just talking about comes into play with these LLMs, with LLM agents, is like, I want to think about like the moves that an LLM agent has as kind of like the thoughts that it can have in its reasoning process and how it can execute on these tasks. So an LLM agent usually it's a system that includes modules for planning, for memory, for tool use, and for retrieval. Usually retrieval kind of gets lumped in with memory, but like that is kind of also includes like knowledge graph based retrieval and stuff like that, which is a little bit more advanced than just having like an agent scratchpad, which is kind of where like some of like the multi-agent frameworks end in terms of what their memory management is. So in this case, we can kind of think of like the overarching goal for an LLM agent to be to complete the user request. And in some ways, it kind of doesn't matter to the LLM agent how it completes the user request, but it has to give you a good answer. And how it defines what a good answer is and how it breaks that into subtasks is kind of up to the LLM agent. And that's where like the engineering part of like this entire thing comes into play. So I talked about like the limitations of LLMs earlier. Here's a not entirely exhaustive list, but a pretty long one. So why do we need to create so much structure for an LLM to solve these kinds of tasks? They have limited single step reasoning capacity, which means that like a complex query, like what is the meaning of life, needs to be broken down into many sub questions, which it may not be able to do like in that single step. It may just hallucinate an answer if it becomes too complicated. But the other thing is that if I ask it like a very complicated riddle with lots of entities and stuff like that, if it has too many entities, depending on like the size of the LLM itself, it'll start just hallucinating like values for certain entities. So if I tell it like so-and-so gave something to so-and-so, then half of it went to so-and-so, and so-and-so did this, and so-and-so did that. After the first two is so-and-so's, it usually starts forgetting what happens after that, or it may only remember the first and the last one. Everything else in between just kind of gets hallucinated for when it gives you an answer. So in that case, like having like a multi-step like problem-solving approach allows it to kind of like tease apart those different pieces of information and then keep it always like within the problem-solving field of view. And then also like it still hallucinates in other ways as well. Like it can sometimes just say very outrageous stuff or just give you like completely inaccurate answers. And so in that sense, like having like the prompt guardrails also baked into like the agentic system helps a lot. And then it also allows us to add real-time data. It also allows us to have some observability into the thought process, because now you can kind of have it say, this is my next thought, this is the thought after that, this is the information that I'm using here, this is how I'm processing this particular type of information, and have it explicitly state that, which allows you to then kind of go through like, what is the LLM's thought process, at least at these individual checkpoints that I have. And then Yeah, a lot of these techniques just fundamentally improve like the ability of the LLMs to the point where even very small LLMs can perform at the level of much larger ones. Like the 7B parameter LLMs using like a couple of these different techniques that I'm about to go through can basically perform as well as like language models that have like 70 billion parameters or more. Which is really cool because it means that you can essentially start running some of these like agentic frameworks on your laptop, but then still get like the level of performance as like you prompted like a big model to do it in one shot, and it may not work as well as like prompting a small model many times.
So most of them are like not just limited only to the agents, right? So it is non-agentic approach also we can take these steps to improve the better performance.
So the interesting part about this is like all the subsystems here, you can still apply any of these subsystems to the language model and then still see like a considerably like better performance. I'm not going to argue like against that point. That's certainly very true. But the way that like these things tend to get like implemented in like the agentic frameworks, like if you're looking at say LangChain, which kind of serves as like a backend for like some of these different frameworks which are there. It's the backend for CrewAI. It tends to be in practically all the examples that you see on the internet. It has agents, but then also like function calling ability, memory management, and like a couple of these like planning, access to retrieval, that's all decoupled from like the actual agentic ability. And in some ways you can like define an agent in LangChain without ever actually explicitly defining like an agent with the agent function that they have, because you're essentially like adding all of these pieces together to get it. I would kind of argue that like what makes an LLM agent is actually the planning portion in particular. So like, is it breaking down something into subtasks? Is it trying to execute like on these subtasks like appropriately? But that kind of requires that you also have like the memory and the tool use involved. And some would also argue that it's like the planning is necessary for an agent and then also the tool use is necessary for an agent. That partially depends on like what your definition of an agent is. So like if your agent is an architecture in a program, it has, or even that an agent is perceiving its environment, that means that it has to have access to tools because it needs to be running experiments. That's just like fundamentally like how many people would argue like an agent should be defined. But yeah, in an LLM context, like that might be a little bit more complicated because it's anyway working like in a somewhat abstract space. Like the LLM is just hallucinating. It could just, from like a stochastic parrot perspective, like you might be asking an LLM to just hallucinate a chain of times and then it gives you a reasonable sounding answer, and then that's what's being returned to you. It's not actually running any experiments in the real world. So yeah, I don't know, kind of like exercise for the reader. In fact, some computer scientists may even argue that like an agent isn't really real unless it has access to like robotic data, which like I don't necessarily believe in, but if you're really hardcore into robotics, like that might be your point of view. Any questions at this point in time?
Sheila, one question. I think the box that you drew to the left, in that picture, the memory. So if you look at RAG and all these, so you kind of a big document is broken down into multiple sections and vectorized and similarity, and then that's picked up. So in the same way, so imagine if the plan comes up, let's say I ask LLM, I'm traveling to Santa Fe, route me the best route, A, B, C, and it gives me a route. Now, so that it doesn't hallucinate, just like I store the parts of the document, it kind of gave me a plan. And if I want to go any further into the plan, do I kind of store the plan A, B, C separately so that I can go back and say, hey, I need to do more things in A. Now let's talk about A, then let's talk about B. So that I don't want it to forget. It gave me the plan, overall plan to begin with. And now I want to go deeper further. It can hallucinate. So just like we are saving the parts of the document, do we save parts of the plan too, so that it doesn't hallucinate on the plan?
Yeah. So yeah, that is part of like one of the things that I wanted to discuss at like the very end of this, which is again kind of an open-ended question, because it also depends on the LLM that you're using here. If you're using one of like the really, really big ones, like you're using like the nicest like ChatGPT model, like the likelihood of it hallucinating is like significantly lower than if you're using like Llama 3 8B. And so in that case, like making the decision, like, should I be storing this information or not? Kind of does, yeah, we'll talk about this a little bit more. Like, how does optimal like memory management look like? Because again, there's not like one clear answer, but like the general approach is that we should be storing pieces of information, especially like at intervals that we deem important in like the task completion into whatever memory management system we have at this point in time. So
can I answer
yeah.
the question? So Llama Index has two things. It has a query and it has a chat call. So if you use a chat call, it automatically stores all the conversation. So you don't have to worry about the memory management in case of using Llama Index. And LangChain has a similar way of doing things. So below the inside that framework, I don't know, it's a black box. But then yes, so I just wanted to state some of them have these frameworks have it built in.
Yeah. So we'll be talking about that in a little bit. Usually like the way, like the naive way of doing it, if you like kind of like keep all the underlying settings the same, is that it has like what's called an agent scratchpad, and it'll like write down like pieces of information into the scratchpad. But there are limitations to this because the scratchpad is like, it has to be something that can be appended to the prompt, like to the LLM at any given point of time, which is not so straightforward if you only have like 8,000 tokens or something and your chat is very long. Right, so you have to start like summarizing what's going on in the chat into like things that are like easier to deal with. And more than that, even if it does fall within the context length, you can't just store it any way you want to and then expect the agent to be able to remember everything that's going on in that context. Basically, like it'll start hallucinating on some of the stuff that's there if it's not organized, if the information is not organized very well. And in that sense, like, yeah, again, we'll see this a little bit later, but there's also part of some of these memory management systems has been to like itemize like the important pieces of information into things that are like easier for the LLMs to be able to process very quickly. So I'm not just going to talk about like, this is a summary of everything that's happened. I'm going to maybe first mention, these are the key people that have been mentioned in this chat. And then I'm going to mention that these are the key decisions that have been made so far. And then I will have the summary for the rest of it, because that allows the agent, like whichever LLM is reading it after that, to be able to kind of more appropriately parse through the summary, and then also know like what previous decisions have already been made. Yeah, do we have any other questions, by the way? Okay, great. So yeah, lots of limitations for LLMs in particular, and agents kind of like deal with different sections of this. The tool use and planning in particular, I would kind of argue like gets lumped into what being an agent is. And then also that's kind of like how different papers have defined being an agent. So like if you look at React, for example, that kind of pretty explicitly says that if I have something that's planning and that is also interacting with the world at the same time, that is an agent. And then other ones will kind of like argue that, yeah, basically you have to have the planning aspect and you have to have the interaction aspect. So you kind of do need both. But chain of thought, for example, you may choose to believe that's not an agent, and I would kind of argue that it's not. But yeah, well, yeah. So yeah, next step is like, what is agentic reasoning? How did we even like come to the conclusion that agents or that LLMs can reason in the first place? I think that is actually really fascinating that they can, given the fact that a lot of these like LLMs have been trained on just predicting the next token, or just like predicting like, you know, like tokens in and of themselves. Like the fact that they can produce like reasoning chains that make sense is pretty interesting, in my opinion. And then that gets explored like through these papers, like chain of thought, self-consistency, tree of thought. Chain of thought kind of shows that like you can take like a bunch of math problems, like this is kind of the approach that they had, like they took a bunch of math problems and then they had like the LLM just answer the math problems, and they're like word problems. Just answering it out of the box showed that the LLMs couldn't do it. Like they just like hallucinate some answer and give it back to you. Like they'd have, I don't know, so-and-so had 5 balls and gave 2 of them to so-and-so. How many balls do they have left? And then like the agent would say 6. which obviously is impossible because the guy started out with 5 balls, and then if he gave 2 away, then he has to have like less than 5 balls. But he gave like the LLM gives the answer 6. But then if you give it that reasoning that, oh, if so and so had 5 balls and then they give 2 away, that means that they have to have 5 minus 2 balls, which is 3. Therefore, like so and so had 3 balls. And then if it was able to give that reasoning chain, then you could give different math problems to the same agent and it would actually be able to answer it because it like goes through the same like reasoning process for every single one of like the new things that was there. So it shows that breaking these like statements into sub problems that can be solved like verbally actually allows the agent to perform much better. And more than that, when you start adding like more variables into these statements, you add more people, you add more objects to keep track of, and so on and so forth. Then allowing the agent, like the reasoning chains to still exist, allows it to keep track of that information much more effectively. So it still remembers that there are, I don't know, 5 entities in this thing, and that they're trading like 3 different like trading things. Instead of just saying like, I'm going to remember like the first 2 entities, and I'm only going to remember one of the things that they're trading, and then I'm just going to hallucinate the rest of it. And then, yeah, another one that kind of goes into what we were talking about earlier with like, how do I choose like the optimal next step to have is like self-consistency. So this paper looks into the fact that like, if I have the LLM come up with like 5 different reasoning chains, actually like the chains that have the modal answer are much more likely to be correct. Oh. Modal answer meaning like the most common answer. If I have like 4 chains that say that the answer is 3 and then 1 chain that says the answer is 2, then actually the answer 3 is much more likely to be correct than 2, because if I got the same answer like 4 different ways, then I think that that's probably more likely to be right than if I were to get a wrong answer like one way. So yeah, so that's kind of been like folded into like many of these chain of thought algorithms, so that I can kind of like marginalize away what I believe to be inconsistent answers with like my own understanding of the world, which I believe are less likely to be correct. And then, yeah, tree of thought kind of expands on both of these ideas, and then kind of says, what if I were able to not only like come up with like different steps, but what if I were also able to backtrack on my reasoning if I find that like this particular chain of reasoning isn't yielding me like a good answer. So when it comes to agents, that kind of allows agents to try out different things, but then also be able to step back and then say like, hey, this isn't working. Like, what if I went back to like one of my previous conclusions and then like went forward from there? Yeah, any questions so far? I know that many of you have probably read these papers already, so.
Hey, Yashira. Sorry, go ahead.
Oh yeah, I think Andrew had his hand raised.
Yes, hi. I guess I just want to give a perspective that you may want to react to and might be helpful, in this conversation, which is that, previously in computer science, we had the issue of creating agents where we have to figure out the steps that are required to reach an end goal. And now we have these LLMs that can reason in some sense on general problems and give us through careful prompt engineering parsable outputs that help an agent perform activities in the world outside of the LLM. And the problem then is reduced to calculating, as you put it, a distance to that goal. The way I think about it is that, sometimes it's hard to come up with a proof or even steps to prove a problem. But if someone gives you the answer, you can very quickly tell that the answer is correct. And so I look at the task of creating an agent kind of like managing all of the balls that are in the air and determining, what pieces of information are still missing and what aspects of the goal, haven't yet been achieved, and, containerizing them in such a way that they can be, inserted into a prompt appropriately, right? And all of those things to me as a computer scientist sound quote unquote easy to do, right? I'm doing air quotes right now. But the overall task of coming up with a set of steps that have to solve a problem, that's the difficult part that I would leave to the LLM. And so I guess I just wanted to give that perspective and get your reaction, because I really look at the LLM component of this and its context, which is this memory that you've been talking about, as a tool that now is the brains, if you will, of the system that's attempting to achieve the goal, but we have a more procedural and deterministic set of mechanisms that are outside of that brain, that are managing the heuristic elements of attaining a particular goal. And that's the way I think about it.
Yeah. I think that that's an interesting input, that like, I think especially the part that you mentioned about like this external apparatus is like basically setting up like the heuristic function for the LLM, like that's entirely true. But then at the same time, it's not like a heuristic function, which is like the way that you traditionally define it, like in game theory, because like we don't have, like I was mentioning earlier, like we don't have a Bellman equation, which is kind of like the super duper classic way of like defining like how close we are to like our output, or like what utility we have, or like what utility a specific action has actually. And that's where I feel like this kind of gets super fuzzy, because like for each of the thoughts that we have, say in chain of thought, it's not like, yeah, I don't know, like in many of these cases, like they're not actually like calculating a heuristic score that looks at like how close things are to the reality of like what I want.
No, and just to jump in to clarify, I'm not suggesting that there's some function that's being calculated by this external system, but rather often if I get called in to solve a problem, I build a program that has many different data structures that keep track of all the different elements of the problem that's attempting to be solved. And I'm not sort of explicitly creating a function there, but what I do know and what I can procedurally do is determine what aspects of the goal are still missing, and perhaps insert elements of the prompt that have been determined by the creator of the agent to help achieve those goals. Right.
Yeah. So this is where I think this in particular gets interesting, is like, we're basically describing like discrete states in which we are like at any given point of time. And even like our our external heuristic is only kind of managing like the discrete states that we can like enter into. And I think like you're totally right. Like we don't necessarily even need to have like a heuristic function, so to speak. And like these systems seem to work super well without it. But I also want everybody to keep in mind, like, what would this look like if we actually did have a way to like generate a heuristic? And also like, how would we go about generating it? Because I think that that's like one of the main, like, that's one of like the main pieces of information, or like not information, but like the main areas of research that's still super open at the moment.
One final interjection, if you don't mind. Could you speak to whether or not concepts like finite state machines have been integrated into these agent systems to date?
I actually don't know.
Not yet, actually. So like this is very like the one thing at least I want to point out is that the LLM agent is not much different from the software agent during the advent of computing, right? For example, if you take a goal-oriented problem, how do you detect a deadlock? At the time, we had the same issues of like how do you handle memory, because memory is still important, and then how do you handle tools? How do you move towards a goal-oriented behavior? At that time, you define like Yashila mentioned, you divide the problem into n set of discrete states, and then how you move about it. Earlier, we used to have like a procedural function which moved towards the goal, but now with the LLMs, the advantage is that fundamentally the nature of the procedure is stochastic. Now you could do two things, right? So the chain of thought, what it derives is that by actually making a particular LLM explain a procedure, through intermediate steps, you arrive at a better procedure. And that's where you're like kind of like a heuristic where you can guide using prompts. But fundamentally, the nature of agentic architecture, so to speak, is very similar in terms of like FSM, deterministic world, or probabilistic FSMs. But here in this case, it's like almost like a stochastic FSMs. So we do not even know how many discrete steps it would take to attain a goal. And that's where actually you kind of allow the LLM to form that procedure. But what we can do externally though is that how do we minimize the inherent problems with LLM, with all of these hallucination and ability to arrive at a wrong procedure. That's where an external heuristics would help. But I think more and more it will evolve into like a stochastic FSM, so to speak, not like a deterministic FSM, a probabilistic FSM, which is what we do in software agentic frameworks.
Correct. So that's the way I also understand. So though the LLMs are stochastic, the agents can decide to wait until, right? I mean complete until they got the good answer. So until then, it's going to keep trying with the different ideas, right? What you can call intermediate steps. So that so the answer to the question, yes, we have to deal with the stochastic nature of LLM even in the planning steps, but we can handle that. Agents can handle that in a way that it can produce consistent results. That's my thinking. Yeah.
No, yeah, that's completely correct. And I also, do I go over this later? Not so much. Okay, yeah. One of the things that I did want to mention is that like this again is one of the things which the current like multi-agent frameworks do to some extent is that they like have the prompt set up such that it's always trying to get the agent to like be going back towards like the goal that you have in mind at any given point of time. So the way that like the prompt is set up is saying like keep in mind that this is what we want to do. But like one of the main questions that still exists is like how much should we force like the LLMs to actually adhere to like what we think like the outputs for the substeps should be? Like, do I want to like very strictly define like what each of the subtasks are and like what each of like the ideal states of like a final output of the subtasks are? Or should I leave that problem to be open to the agent? Should I allow it to kind of like define all the subtasks and substeps and like all the sub goals by itself? So if you look at say like AutoGen, or if you look at like Creo, or if you look at like several of like the other, like even like LangChain agents to some extent basically do the exact same thing. For each of these agents, they have like a super specific task which exists within like the super task which you assign to like all the agents together. And then you also have like very like strictly defined outputs for the task that you need to have. And so that helps like the agents both communicate with each other and then also like get to like the output that you want quickly. But what if like the workflow that you define for the agents is like not the most optimal way to do so? And that's where like some of like the other like frameworks which exist kind of argue that you shouldn't be doing it that way, that you should allow like the inherent intelligence of the LLMs to kind of take over and do the planning for you. Which is probably not a bad way to go about it if you have access to one of like the really big LLMs that are there. But yeah, so for like the smaller agents versus bigger agents, like argument, I would say that like smaller LLMs require much more guidance in terms of like completing subtasks because they are not really capable of planning at a very high level. But at the same time, if you again have GPT-4, like it can do lots of this planning even in a single step. Like if you look at say like GPT-4 and you give it like a bunch of code and then you ask it to like fix the code and give you like an explanation for it, that would take like, you know, like Llama 3, for example, it might take it like a few prompts to get to that conclusion, but then GPT-4 is able to do it really well, like in one go. So yeah, but then you could also argue on the other hand of that is that if you give it that freedom to do that, its performance may not be consistent in the same way that you would want it to be for like different use cases. So you may still have some advantage to having the small agents is like even if it fails every once in a while, you always know that it has a certain type of output. Whereas with like the larger models, you may have like radically different reasoning chains like in different steps for whatever reason. So you may have like the same answer like 5 different times, but it gives you a completely different reasoning every time. And then that may not be what you want to see like from an agent at any given, for whatever reason. But yeah, again, I feel like it's an interesting open question, and then also like trying to define. Yeah, I mentioned earlier that like still like this heuristic is not defined in terms of like an actual like numerical heuristic. Like it's basically assuming that this is a discrete space, even though the outputs for this are like a little bit continuous, because like you can kind of generate many different versions of the same statement. And actually is one of those versions of the same statement like better than the other one? I don't know. I think Karthik also had an answer or a question.
Yeah, actually, I haven't read both of these, either of these papers. So just trying to understand what's written over here. Like, what is the mechanism in which these several reasoning chains are actually generated? This is just increasing the beam size for the token generation, or like running the same engine with different temperatures. So that's one thing. And the second one is how does backtracking work in the context of next token prediction? Like, how does that work? Because you are essentially saying that some parts in the context, overall context that you see, should be given very low attention, so to speak, and then focus on the rest. So I'm just curious, next token prediction setting, how does backtracking work?
So in this case, actually, I think it's not next token prediction, which constitutes like the thoughts in tree of thought, for example. It'll like generate an entire statement. Like, however, I actually don't remember how that's defined. And I don't remember exactly like how they made the decision as to like, or like how the tree of thought algorithm makes the decision to like backtrack. But I think it's like when it goes on for like a certain amount of time. Yeah, I don't remember. So if anybody knows, like in the audience, I'd really appreciate if they could answer. Yeah. So in this case, the statement which is being evaluated is like an entire statement. It's not the next token, and that's kind of like going into like the heuristic thing that I was talking about earlier. Because like in some statements, if you like change the words slightly, you can have like a pretty dramatically different meaning. And so in that case, like, how do I evaluate, even if two statements sound very similar, how do I evaluate like the difference between those two statements? Can I actually make a heuristic for that? That's a little bit more, that's the kind of finicky part about like the slight differences in like the generated outputs.
Okay, the sub-consistency will be a skill for that one, right? Because if you get like 3 or 4 answers, the probability of like 3 is good, then you can you can refer that one because
exactly. So like in some cases, I think that's actually how they do it, is that like for the self-consistent answers, you can kind of like map out potential answers that exist already that like lead to the same output. And so then you can kind of like look at like a new generation that goes through like you want to get the same answer like from like the same like question. You can then kind of like map out like what is like the vector distance between like any given statement and the previous statements that I know to be correct, like for this particular step. But again,
these are assumptions, so basically
has
to verify that.
So
I mean, maybe the intuition, like I haven't read the paper as well, but the intuition is something like this, right? Imagine that you're trying to solve a crossword puzzle, and then there are let's say two ways to go about it, right? So let's say there is a set of questions and a finished crossword puzzle, and more crossword puzzle you look at like that, and you would be able to gain an intuition or like a mechanism or procedure how to solve it. But what chain of thought and tree of thought kind of figured out is that instead of actually just simply giving you a set of crossword questions and puzzle, if I show you like a different state of the crosswords, like step 1, I start with maybe cross, always finish the crosses or top down. And then once you have that, so then there are like 5 different people can solve crossword in 5 different ways. All of them can arrive at the same answer. But if more and more different ways of actually showing intermediate state going towards it, that's how the backtracking works. So backtracking, basically chain of thought initially said that instead of just showing a set of like crossword questions and puzzle, if you actually show the LLM with the intermediate steps, if you feed it and train it, then actually the chain of thought produces better results because it understands in between steps. And tree of thought is just basically generalizing it, not only showing one particular way, if you can show n number of ways of actually achieving the same answer, then you actually introduce, like, it's basically how the 8 points or n points problems are solved in a deterministic way. Now you just generalize it in a stochastic way that if 10 people or 100 people or 1,000 people or 1,000,000 people can solve the same crossword puzzle in n different ways, then you can actually backtrack and create a thought tree, like how this should proceed. At least that's what my intuition about tree of thought.
Yeah, so with self-consistency though, I think that the way that they do it is literally that it has it generate like the whole chain from start to finish like a certain number of times. And then all of like, so when I say like modal answer here, I mean like the most common answer. Like it is the mode out of all of the outputs, right? And in that case, like every other answer aside from the modal answer is just assumed to be wrong. That is like one of the assumptions like from the paper itself. But if you have like situations in which the answer is not so clear cut as like there's only one answer to a question, then this kind of falls apart pretty quickly. But the idea is essentially that like if you want to be consistent with your own thinking pattern, and so you're always going to like force yourself to be like less stochastically variable, which is actually one of the things that we want for agents. Even if the agent is wrong, like in 5% of the cases, it's better to know where it is wrong than for it to be just like really randomly wrong in 3% of the cases, right? And so in that sense, yeah, there is some balance between being right and wrong, but then at the same time, like it's better to be self-consistent because that makes it easier for you to engineer solutions with. So yeah, so there are like many combinations of chain of thought, self-consistency, tree of thought, many other like chain, tree, whatever of thought, like things that are there, and implementations and integrations like into agentic frameworks. And the next thing that I wanted to go over is like kind of like tool use and then moving into tool use. And I know that it's like 8 p.m. so some of you are probably gonna have to go soon, but I'll try to make it to at least like agentic memory, and then we'll the rest of the conversation.
Hold off on the questions until I do complete the presentation.
Yeah. Okay, yeah. I'll kind of like go through this. And we've talked about a lot of this already, so I think it should be fine. Yeah, so one of the other parts about like planning is, especially with agents, like when you're practically defining it, a lot of agents are like heuristically oriented. And so like in those cases, you need to be like getting inputs for the actions that you are making in order to be able to figure out, am I actually making the right decision? Am I moving towards the goal? And so in that case, like we want to integrate tools into LLMs, not only to like give them more ability, but then also for them to verify that like the planning steps that they're making are consistent with like the existing worldview of like everything else that's there. So like React kind of creates like, it basically like pairs like actions and observations. So every time like an action is made, it'll like record an observation and what they call like an interleaving pattern, so that it can like inform like the planning that happens there. This isn't necessarily the paradigm that's used with all of like the agents that exist. In many cases, they'll have like a few planning steps, mostly because the agents may need the planning steps in order to like generate a good action to take next. But then essentially like at the end of like the planning stage, then it'll propose an action, choose one of the tools, and then execute on that tool, gather some information, and then continue with the planning. And so chain of abstraction is an interesting one that I wanted to go over in a little bit more depth, but then I didn't really have the time to kind of go through it very fully. Although maybe I originally, when I planned this presentation, I wanted to have like an example for everyone, like integrated through Llama Index, because they actually made a few of the agents like from these papers into actual agents that you can then call from Llama Index and then like kind of use with the rest of Llama Index, which includes like the RAG frameworks and everything. Which I thought was really cool, because then that can kind of, we can start asking questions from this presentation, like how does this type of agent work versus that type of agent? How do we see these things like with the perspective of like how we define agents more generally? And are we able to figure out like what these agents are actually better at than other ones? But sadly, I kind of ran out of time with making this presentation, and also it seems like it's a very long discussion anyway, so maybe we'll do it another time. But yeah, chain of abstraction I thought was really interesting, because it actually creates like abstract reasoning chains, which are not like, when you look at tree of thought, it's actually like generating text, which constitutes each of the thoughts. according to like what I read through like the abstract for chain of abstraction, and also a little bit like into the paper itself, like the reasoning chains are like not just text. It's like actually like abstract like tokens that it's like using to represent what I guess like the symbolic thinking is for the planning here. And then the idea there is that if I can think symbolically enough, then I should be able to use like this like chain of abstraction point of view with like any type of like actuator or any type of like tool set that I'd be interested in using. Which is really cool because then you can start like taking a very similar like agentic framework using like chain of abstraction and then like applying it to like, I want to make a robot and I want to just like have it run with the robot, right? So yeah, an interesting paper. And then it also still interleaves, like it's also still based on React. So it's like still interleaving like the action observation sets as well. And then the cool part about this is that according to this paper, it reduces like the tool use such that like chain of abstraction works like 1.4 times faster than like the React agent that they were comparing it to with like the same LLM and everything. So apparently by using like the chain of abstraction, they're able to kind of like simplify on the actions or like the planning that's involved in like taking actions. And then that allows them to like use tools more efficiently or maybe even plan more efficiently. So I thought that was an interesting paper. It might be worthwhile to like actually go in depth on it, but yeah. So we don't want just planning. We also want these agents to be interacting with tools. And then there are more reasons for us to use tools than just verbal, just like getting information. The other big thing that's kind of an issue with LLMs is that the verbal reasoning is really good. Non-verbal reasoning is kind of bad. And that's mostly because most of the data that we train on it is like either code or in many cases lots of data, or it's just like verbal reasoning, like it's just straight up text. So if you try to have it do like mathematical problems, in most cases, if you take an LLM out of the box, like it's not going to be able to answer a math question very well. If you give it a calculator, however, it's really good at formatting inputs for a calculator to get an answer out of a calculator and then use it abstractly, which is part of the reason why chain of abstraction works, in my opinion, is that it can deal with the tool as an abstract concept and then format the inputs for the tool as abstract entities, and then take the output from the tool and then deal with it as an abstract entity as well. So that's really interesting because then this is kind of like how a lot of like the agentic frameworks work, even though like in like research, they kind of deal with tools a little bit differently in some of these papers. They essentially like create function calling such that the LLM is just extracting entities to like toss into like a function that has been predefined and has like a specific set of inputs that have already been predefined by like the, in many cases, it's actually like by the comments that exist like in the code itself. Yeah, so, or actually the decorators for the comments, but yeah, I thought this was kind of interesting because it means that like the abstract thinking of the LLMs is pretty good and so is the verbal reasoning, but like one of them, yeah, going back to the point here is that non-verbal reasoning or like specific use cases which are not verbal reasoning are like you basically need a tool for it. And more than that, the other interesting part about this is that it offloads some of like the thinking that the LLM has to do onto like an external thing. So if you're doing like a matching algorithm, for example, or like a recommendation system, you can have the LLM produce like a most likely recommendation for you. But it actually causes like it can induce hallucination in the LLM. So if I say like I want to, and this is actually a project I did recently, I want to meet my friend so-and-so over the next week. And then I have like my availability, my friend's availability, and then our shared interests. I can actually get an LLM to give me an answer, but then if I ask it for 3 answers, it may only give me 1 answer, which is actually true. And in this case, if I allow the LLM to use like a schedule matching tool that shows when are we free for a 2-hour slot, and then also what are our shared interests, then if it has that information already, like the shared availability and then also like what our interests are, then it can generate really high quality suggestions for when we should be meeting. So LLMs are great at like making suggestions, and they're also even good at making recommendations, but depending on like the quality of the LLM, it does actually hallucinate unless you kind of structure some of the information that goes into it. And so that's another reason why you would want to use tools, even if the LLM is capable of doing a task, that doesn't necessarily mean that like it shouldn't be broken down into like more discrete subtasks. And offloading those subtasks like onto functions is usually also computationally cheaper than having the LLM do it for you. Yeah, and then out of distribution data is another good reason for this. Like if I want to search through like online content, for example, like I can enable an LLM to do that through function calling. I can give it a scraper, which is cool because then you can enable it to do all kinds of things with that. And then the last point that I had here is that some of these LLMs are actually, or like some of the papers on this are doing some interesting work by essentially having the LLMs define what the functions should be, what the inputs should be abstractly, but then not actually executing it. Like it essentially will like write its own code and then tell you, oh, this is like the chain that I have for like what my reasoning is. And then if you execute this piece of code with these inputs, then the output you should transform in this way. And then it'll give you like a good answer. And then it apparently works pretty well. That's kind of what these two papers say at the bottom. Oh, Andrew, I'll just go through agentic memory really fast, and then we'll basically like do all the questions and stuff, because I know it's getting late for a lot of people. We talked about like the motivations behind agentic memory quite a bit. We have like the context length is one of like the main motivations. If you have an LLM that only has like 8K like tokens as the context, then you may not have, you may have like a chat that exceeds that length, and in that case, or even like content that you are interested in like using for the LLM that exceeds that length, and in that case we have to kind of pre-process it so that we can fit it into the context. And then we also, as I was saying earlier, it's in some cases it might be necessary to like prioritize context information or like format the information that we're passing into the prompt so that it's more accessible to the LLM. And then also agentic systems in particular, especially ones that use like smaller language models, start to generate like really long context very quickly because they're talking to each other a lot. They essentially will be constantly asking questions because they have like a very limited amount of like, I guess like in agent memory or in LLM memory. It's kind of like if you have like a bunch of toddlers that like can only remember like 3 things, as opposed to like an adult can remember 16 things or something. Then if I can only juggle 3 things at a time, I would constantly need to be asking questions because I'm going to keep forgetting like what I'm actually working on and what I should be doing and like what is there. And in that case, like if I'm constantly asking questions, my context length is going to start growing really fast. And if that is the case, I need to start like really aggressively summarizing like all the stuff that I've been talking about before. And so most of these implementations kind of allow agents to write in a scratchpad, which is then appended to the prompt window for the next reasoning step. I think that this paper, if anybody here knows me, then you probably know that I like this paper a lot. I also know the people who wrote it, and I think that they're really cool. But this paper, MemGPT, develops like this idea of like virtual context management in a very similar way to like virtual memory management. Where if you're kind of thinking about like what's sitting in the context window, like for your LLM as being kind of like, what is like the level 1 memory that I have available like to a CPU? Like how am I kind of like booting things, or like how am I kind of like managing like my context so that I have everything that I need immediately available, and then I'm also able to like page it really fast if for whatever reason like I have to kind of kick it down to like level 2 memory or like further down the thing. In such a way that to the LLM itself, it's like kind of seamless that I can just kind of like grab the information as I need it. And that's kind of where like some of these systems, like we just talked about the agent scratchpad, but like that's where some of like these RAG systems and especially the knowledge graph RAG systems kind of come into play, because then you can start thinking about like context management in terms of like hierarchical memory management, where like there are certain things that I might actually want to have on hand all the time. So if I have like an assistant agent for a person, maybe like the personal information about that person is something that's actually really important to me like most of the time, because practically everything that I'm doing has to do with that person, or other similar things. And so in that sense, like creating like a good algorithm for agents to populate these RAG systems or the knowledge graph RAG systems by themselves is like another open topic that is really interesting, because it seems to be that like when agents are given access to like knowledge graph RAG, I know that like we went over knowledge graph RAG recently as well. I don't think I was there for that session, but some of you might have been. But yeah, that giving them access to like graph RAG systems makes them like really good at being able to query information. So yeah, that also improves like the ability of the LLMs quite a bit. Oh yeah, and the multi-agent systems, like really quick before we jump into discussion. Yeah, so now that we've talked about single agents, like you can also now start defining multiple agents that can be working in concert to like execute super tasks. So you can have like one agent that's really focused on doing like one particular task. And then you might want to chain together like different agents like working in a workflow so that they're either continuously executing on a particular task and then always giving certain types of outputs and then communicating those outputs to other agents. Or you might want to have like agents which are like very clearly defined for each of the tasks in a workflow that you've predefined. And again, this kind of goes into like the discussion that we had earlier, like to what extent should we be defining the workflows, you know? And then, yeah, you can also have like agentic interfaces that are kind of like APIs for agents. If you have like one big agent that's doing everything for you, it might still need to be communicating with other people's big agents. And there you go. There you have it. An overview of agents, although we didn't get into implementation. Yeah.
Actually,
And
one question, if you don't mind. So just more of a, I would say, just a wording or context. So before, the multi-agent, before this slide, whatever you covered, whether we call it as an agent or a simple, RAG, client, it seems like it's the same. Do you see any different? Multi-agent is different, right? In other words, multiple agents working together to finish some task. But let's for a moment, before the multi-agent, the concept we covered, the planning, the memory, right? All those things. It's the same as concept for, which usually we do for chatbot and, RAG-based client applications. Is it correct, or my view is wrong?
I think that like the key difference between like a RAG application, like a RAG chatbot and actually like a proper agent is like how that it has access to planning and that it has access to tool use. If it is a chatbot that has both of these things, then I think it can be considered an agent.
Okay.
But one of the main things though with like the chatbots that are there is that in some cases it's just generating off of like the underlying material, right? Like off of like the RAG system that exists. And in that case, it's not doing any planning. It's just kind of like processing information that's coming out of like a database.
All right, makes sense. That's a good way to put it. Yeah.
Which one?
Go back to the diagram.
Yeah, like the
Yeah.
point that I was making
So
earlier
if
is
you
that
take away the tool and the agent, that is a naive graph.
yeah,
Naive RAG.
yeah,
So that's what you're doing. Taking the user request and read to that. No, sorry, it's like a planning as well. User request, agent, and memory. That is a naive RAG. But adding the tools and the planning, which we are giving some sort of like a responsibility to the LLM, and making
Then it's becoming an agent.
yeah. And in this case, I know Andrew, you've been meaning to ask a question for a while. I'll just answer this really quick. I also think that like RAG kind of falls in between like a tool and like a memory thing, because like if you're really strictly defining this, I would maybe even add like a fourth one, which is like access to like external databases, and then memory being explicitly the Scratchpad. Where like in theory, like querying off of a database in some ways is kind of like using a tool, because you're like verifying that like your planning actually like is consistent with the existing information that's in the database. But yeah, it's again, these definitions are a little bit fuzzy.
Yeah,
they're-
even like for calling the tools, right? So you need to do the formatting for the tools, what you're going to call. Like take
Yeah.
the word example, the calculator example, right? Instead of calculator example, if you take like an analogy to making a call to an weather API. Right?
Yeah.
So which means that, okay, given that information, you have to format that information according to the API contract, right?
Yeah.
So which means that, okay, you need to have some sort of like a planning as well as like the format.
Yeah, exactly. Yeah.
I know it's just a word, I use our words, right? Right now, for example, some of the chat application I'm building, we don't call agent, but it has a planning, it has a access to external tools, it has memory, but we still call it as a conversational chatbot. That's how we're naming it. So I'm just saying that, yeah.
You could consider it as a retrieval agent. At the end
Yeah.
of the day, what you're trying to do is you retrieve information, probably summarize it, and then for that you do I mean, agentic framework just gives the architecture of like, instead of like, imagine that you have like 100 such chatbots across 100 different companies. Now I have a generic question. How do I now invoke a particular chatbot depending on the context of answer generated? Then you could think about like an agentic framework that involves like complex planning.
Perfect. That's what I said. When it goes to the multi-agent, I agree, right? I'm then going into the actual agentic reasoning or framework. Yeah.
Maybe Krishna, we can take it offline. So, but I think like planning how you are doing would be, is not, you are asking the LLM to do the planning in that case. So if you
in my case, I'm asking, just for the example.
Okay, then you are already like building agent.
Yeah, but we are calling that.
Yeah, it's usually called, I think some of them are, we started to call them retrieval agents instead of like chatbots, because chatbot is only, but what is the goal of it? Is it to engage and present relevant information, or is it to actually find out the relevant information? So depending on it, it becomes like either conversational agents or retrieval agents.
So I think the comment, I'll jump in for a second, the comment I've been waiting to make, which I think is relevant to this conversation, it's both a comment and a question in one, is if we consider the term locus of control, which is used in psychology, right? We can say that we have an internal locus of control or an external one. I think what's relevant to this discussion, and as this vocabulary is being built in the industry, is where is the locus of control, right? And the implicit question I have there is, because I haven't read all of the same papers that you have, in general, is the locus of control in the LLM, or is it in an external system which is driving and using the LLM? This relates to my prior comment as well, which is driving and using the LLM to reach a particular goal. And I would see a chatbot being distinctly different from a system that we might call, or we might say as having agency or being an agent, in that the locus of control in a chatbot is the person chatting with the chatbot that is actually driving that chatbot to give more information or to fetch and retrieve and perhaps even do things, but the human is kind of where the locus of control is. That's all I had to say.
Interesting. Yeah, no, I feel like there are like two different dimensions of this. Is like in a particular interaction, I would argue that the best way to define these systems is such that like the goals themselves are being defined by people. Like the overall arching goals should always be defined by people because they're the ones who will be using these products. And I guess this kind of like one of like the discussion points that, oh, I forgot to add that, but like one of the discussion points that I wanted to have is like, yeah, like LLMs in general have like the ability to parse through like tons of information and also have the ability to structure unstructured data, which is actually really useful for people because it's like you can essentially like have like a huge like, I don't know, table, and then you can have the LLM read through the entire table and give you a summary. Like that in and of itself is actually really cool to me. And I also feel like a lot of people would find that ability very useful. But when we start thinking about like how do we develop like applications which use LLMs, which use agents, which use like any number of these technologies, like what should we actually be using it for? I think that like generally I would kind of argue that like fundamentally we should be using it to structure data, like especially unstructured data, because like we would not be able to process data at the same rate that like these systems would be. So it's kind of like if you were to do like an economics type of like reward function on this, like we'd get a lot more utility out of these things if it's processing the data for us. Automating certain types of workflows kind of like goes into the structuring data part of this, is that if you have to like do a set of actions over and over again on like different disparate sources of data, there's no point in having a person do it if you can guarantee that an agent is able to do it as well as a person can, faster, and then also at a larger scale, and then with some more like tweaking and some more engineering, potentially even more with much more stable behavior. And then we can also like generate complex, I say data here, but actually it's like content. So you can start like generating like reports and stuff like that on top of all of this, or even like summarizing information and then sending it out as a JSON like to another database that I can then like pull from to like create, I don't know, a dashboard for someone like in like a corporate context, or like so that I can kind of like summarize what happened throughout the day like on my security camera in front of my house for me. So that allows us to kind of like summarize information and like bring actionable information like to the forefront for a user. And in that sense, I feel like from an engineering point of view, a lot of like the minutia of like how this gets done is not really like an interesting thing for the user. But like there still exists the question of like, as a developer, how much am I willing to give up control like to these individual agents versus like how much am I going to define the workflow, even if it's suboptimal, so that I know that it performs a certain way? I think that kind of like leads into your question very well of like, where's the locus of control within an agentic system? Whereas I feel like if it's like a chat situation, I feel like the locus of control has to be external. And then I also would argue that in many cases, like the user requirements are kind of what will define like what happens in the application. But yeah, internally, like how do I kind of like negotiate like how agents interact with each other, how strictly their workflows are defined, and then also like how does this relate to like agent size and stuff, or like model size and stuff like that? I think that is a really interesting discussion like that we can have right now, and also I think that people should be thinking about more generally.
Exactly. I mean, even
so one thing I feel, Yashila, is that your earlier slide actually brings back some of the differences between a basic chatbot. Well, the chatbots now could also be like agents, but the term agent in AI has been even before LLM. It's generally defined as an entity that perceives its environment through sensors and acts through actuators. Yeah.
I think has been consistent since the first publication of this book in like 95. And also this draws on like all of like the game theory stuff that was kind of developed in like the 50s and 60s.
So a chatbot is not, as after taking actions, it's not checking how the environment has changed and moving to the next thing, actually. So, but an agent can do that. It can backtrack to see how, if it takes an action, what will result into that. Before committing that action, it can see that I'm going on a different chain of the tree of thought. It needs to backtrack. It would do all of these things. So
yeah, but that is also a little bit of a relative statement, because like even if it's not explicitly like even if it's not writing into a database, it may not be fully aware of what's happening in the database. And so if you're looking at an agent, it's still like from like even a robotics perspective, it's still considered an agent, even if it's just moving around on a map, even if it's not touching anything that it's like walking by. And so in that case, like like acting on the environment through actuators in this case would be like navigating through the data that's in the database. Even if it's not interacting with the data on like the level of I'm going to change the data and see that how that affects the database.
And also, about memory, right? Nowadays, conversational AI chatbots also have memory, if you want to say that. So I think, in my opinion, agents means it does maintain a state, and then agents, it can go back, and then it uses a state as one of the way, I guess, for determining the future actions. That's a traditional agent, in my opinion.
Yeah, so like or like trying to perceive the current state, and then also like perceiving its environment and then perceiving the state is usually considered like kind of the same thing. But yeah, like an interesting part about like if you have a chess bot, for example, is that they train a lot of these bots by like running games against itself, right? And in that sense, like if you're a person who's like thinking about playing chess, that's essentially like playing tons and tons and tons of chess games like in your head a little bit. But it kind of like is gaining information through, it's gaining information through making all the moves, but in some ways it's also just kind of like simplifying the strategies by like imagining many, many different goal states, or like many, many different like game states to try to see if we can get to a goal state.
Yeah, my perspective on this is that it's a bit fractal, and you can start to split hairs as you kind of parse the semantics of this, because the moment you're talking about the environment as being a virtual environment, not the actual, universe we live in, the information environment, and actuators being, manipulators of that data environment, then, many things can fit this description of what an agent is. But we might say that they're trivial agents because, something that simply, reverses a string is in some sense, modifying the data environment through an actuator, but that's not the sense in which we want to say it's an agent.
Yeah, I was looking for like my copy of, is it here? Here it is. There are actually like a few different definitions of agent, which they give like 4 definitions for like an agent in this book. Reflex agents are like one of the agents, and that's exactly what you're describing. It like just takes in like a particular state, and then it always does like the same thing. Like it doesn't try to do anything like fancy. It doesn't try to like interpret any of the information that's coming in there. You just have like a predefined policy and you execute on that policy, and that in and of itself is considered an agent, even if it's not necessarily like an intelligent agent and it's not necessarily a rational agent. So yeah, it can be many things. And I also feel like to some extent, like there may not be a lot of like utility in like continuing to.
Right. And also another angle, right? What is personal agent? These vocabularies are evolving. Agents, then I'm thinking, right, there will be a different definition for personal agent, what that means, versus you saw that sales agent, correct? I mean, there was some company did the sales agent recently. So to me, the agents and the workflow and then multi-agents all together is what's shaping up, though we are still trying to learn some of the vocabulary behind that as we go.
Yeah, exactly. Also, I'm like reading through some of like the chat because I just realized that there was.
So my question is, you think this definition still fits? This may be a little, like in our 20 years back definition. So do we still need to carry over this in this LLM world?
I actually think that it's useful in some senses because like defining an agent in this way actually also allows us to start thinking about like there's tons of theory about agents that exist, but almost all of it is like very theoretical, and it kind of like assumes like certain like qualities of the underlying agent. So if you have like a utility based agent, for example, you can start making like a lot of arguments about like how do we define the optimal policy, like what equations can we use, like how do we like create like different evaluations for like how well the agent is performing. But then I think that actually the more interesting part about this is like there's a lot of research in like economics that looks at like the behavior of rational agents like in a market. And actually like for these agents that we would be making like over the next few years, we're probably going to be making agents that interact not only with people, but also with each other a lot. So how do we match agents that have similar goals together? How do we like set up markets for agents? Or like basically like if we're looking at making an agentic platform where like agents are talking to each other, I think it's worthwhile to start considering like agents from like an economics perspective or like a macro like game theory perspective, because then you can start thinking about like matching markets and stuff like that. And then also like how do we set like global goals for like agentic behavior? Which I think is, yeah, like not only do we have like the agent's behavior like at the agentic level, but we might also want to have like desired behavior like at the global level across all the agents at the same time.
I've been thinking a lot about this topic in the sense that as we begin to release these agents into the wild, we're going to have more and more instances, as you just mentioned, of automated systems that can now reason and deal with information in a unstructured way, which implies that there doesn't have to be an interfacer, particularly not a human interfacer to build, the interactions between systems. And so we'll probably end up finding instances of causal loops that come up. Think of an analogy, for example, like in old email systems where you could get into a mail delivery loop, right? Where one agent tries to get to a goal and the other agent sees its activity and tries to get to another goal, and the first agent sees that and flips back to the prior state, and they get into an infinite loop that uses infinite resources and no one ever notices, right? So I suspect we're going to see technologies that have to emerge to, manage resource utilization as agents proliferate the information space.
Yeah, I
Yeah.
agree. I also think it's not necessarily limited to like economics like points of view. I also think that like if we think about I don't know, security like for servers and stuff like that, like we could very easily like propagate misinformation like with agents because they're not very smart beyond a certain level. And so at that point of time, like you can kind of think about that in terms of like how do we deal with security breaches like in a network? Right? Or like how do we track like spread of like a certain type of behavior like across the network if it suddenly starts like go off the rails? And then also how do we predict like when something is about to go off the rails? I don't think that these discussions are necessarily like mutually exclusive, but I do think that like your perspective is like kind of hits the mark a lot in my opinion, where even if we made like individual agents for like small scale use cases, when we start scaling this technology up, then we're going to start seeing like all of like the ugly problems that we're now going to deal with, which are compounded, like the difficulty of them is compounded by the fact that these are still like highly stochastic machines. And it's pretty difficult for us to, it's difficult for us to understand, like to predict what it's about to say next here on a small scale. It's even more difficult to predict, in my opinion, like how these agents are going to behave like with each other en masse. But yeah, I don't know. I think it's a fun subject. Like there's going to be a lot of learning for all of us over the next like couple of years.
Right. It's true. It's very true. I mean, it's agents in the wild. What is going to be the guardrail? Is the guardrail actually provided by yet another agent?
Yeah.
It's like a student-teacher model. I mean, what is the guardrail, and where does the guardrail come from, and who codifies the guardrail actually?
Yeah.
Yeah. So in terms of performance, because it has to go through like many different layers and the planning, chain of thought, all these things. So in a real production use cases, what is the latency?
Yeah.
Because, agents are good. Like there's planning, these, that, and all this thing. But
the latency of it is actually kind of like a lot of people have different opinions on it because like I don't know. I feel even Kishore might have like a better answer for like how inferencing like these LLMs might work. But essentially like
in terms of like the inference time, it has to go through many layers. Now we have like adding more and more capabilities in the system. So which means that it is going to add into that the response time.
Yeah. That's why I think one of those. So if you see the tools which are, the chain of abstraction is a very, very useful paper that actually came out of this approach. Basically, what they initially figured out is now fundamentally an LLM is a stochastic framework. Now, but if you know, it's like giving if you ask a graduate student to take an exam without a scientific calculator, he could do it, but he's wasting a lot of latency of the computing power in actually figuring out if you give him a calculator, which is a tool which reduces the latency. So the chain of abstraction, what it does is that find out all the procedures which we have figured out how to deterministically or probabilistically do it. There we are taking out the latency. Now, when you deploy an inference server, leave only the part which we cannot figure out using deterministic mechanism or a probabilistic mechanism to the stochastic model. And even now there is a recent paper which is called like a mixture of like million experts. Mixture of experts. So earlier the problem was that you could not scale mixture of experts beyond certain number of experts in because easily added. I think it was like a very recent paper, like it just came out last week or something, where they successfully scaled out to millions of experts, and that way, how do you manage the latencies? It's like one of the very keystone paper in inferencing, which kind of reduced the total level of inference. But the idea is this: so how do you make how do you, I mean, you have a complex problem and you want an agent to solve the complex problem, but within the complex problem, we know a lot of like deterministic pieces which we could help. So now you introduce tools which can, and then now there's not only tools, there's also distributed tool approach. How do you distribute in advance? I mean, so one thing I want to point out is that all of this, what we are discussing, are not new. When the advent of computation came, we have exact same issues. Like how do you make, like how do you give your finance decision to a banking program, which then acts on behalf of you? You just authenticate, it actually does, everything is digitally done. But the key thing is they are deterministic, and there's a security paradigm and sandbox and all of that is done. Here, the fundamental intuition is what is the difference between a probabilistic agent and a stochastic agent? And then every time when we deployed a particular software program or software agent, we came up with a schema, and we came up with an API, and we came up with a standard. How a particular software agent that needs to be deployed, how your banking should talk to your credit card, and then all of your object-oriented interface goes to the standard. Similarly, this will happen, and the same problems happen with how are you going to run a fluid mechanics model? Now the same thing, like if you run a fluid mechanics model on a supercomputer, it's pretty fast. But now you could run it on your own computer as well. That means how do you subdivide the problem? How do you distribute the agents? How do you make each agent stop in a software agent? Now the same thing is happening here as well. Earlier also, I think most of us are familiar with deterministic approaches. We are all have grown up with computation, and so we take it for granted. But there are a lot of like probabilistic approaches. So imagine that I give you a problem of or a game of like I've hidden food in a forest. Now you need to write a program to find the food. Now usually people do like a lot of random walks. A lot of like this is where the exploitation versus exploration comes up, which is very similar to how much do you allow an LLM to hallucinate versus consistently, because you want LLM to hallucinate so that it can explore a bit more, more creativity, but you still want it to be consistent. Now, because you are giving a lot of responsibility to the agent. Now,
and this is also where like the second part of this comes in, is like also like what is the size of the agent, or what is the size of the LLM that you want to use? And in this case, you would use small LLMs. Like it's better to use a small LLM, which you can run on a much smaller server or like inference cluster, for simple, straightforward tasks, or for tasks that like still require like some level of stochasticity. You may not want to have the same answer every time, or you may like it may be computationally like somewhat difficult for you to just like write all the code for it to begin with, or for whatever reason you can't predict what the inputs are going to be, and so you believe that the LLM is going to handle it better. And in that case, if it is a straightforward task, you would use a small LLM. But that LLM, like the small LLM, will not be able to like deal with like many complicated subtasks at the same time. Like, and in that case, if we have like a more complicated task that needs to be broken down into subtasks, the subtasks are like pretty clearly defined. If you like know ahead of time that this is the best way to do it, then you still may want to use like a chain of small LLMs. But like if you start chaining those together, like you will start getting really long chats, and you will be calling that LLM many, many, many times. So at some point, if like the task is complex enough, it's actually cheaper for you to run the big model, like for you to properly just like bite the bullet and like run like an API call against like ChatGPT or something like that. I think my computer just ran out of power, but I also sent you guys the link to the and let me know if you can't access it. But I think I sent like the link to the.
Maybe you can drop it in the.
Yeah, I'll drop it in the Discord when I power this back up, but I also put it into the chat. Yeah, and that's where there are also some theories around like how that looks like in multi-agent frameworks. Generally speaking, they believe that you should use larger models for planning, and then also smaller models to execute, especially if you're dealing with text data. So and these, in this case, like in many cases, the data that you're dealing with may still be optimal to like run it through like a model, not necessarily just like an LLM, but even like if you are trying to like interpret like visual information, like running it through like say segment anything, whatever, to kind of like parse it for like syntactic visual information might still be better than like using like a ResNet 50 model or something like that. And then that is also something that you can interface through like these agents, basically. And then if you're trying to like summarize like text, like you're not really going to find like a better way to do it than to do it with a small LLM. if it fits within the context window and if your prompt is not too complicated. But for really complicated planning tasks, I wouldn't bother trying to use like Llama 3. I'd just like try to parse out what should be done very explicitly, like with a big model, and then run those subtasks with a small model so long as I can.
So that's where the mixture of experts come into picture.
Yeah,
right? So
exactly.
you can deal with the which model is that you want to update
Exactly.
lowest computational and the memory constraints.
Yeah, and like the part that comes into this, which is like still kind of the interesting thing, is that like if you do it that way, will you still get consistent behavior if you run the same task 100 times? And that's where I think this kind of gets a little bit more complicated, is that it's not just about can I experimentally get it done once or 10 times. If I'm running this call hundreds of thousands of times, am I actually able to predict the failure rate, and can I predict where it fails? And not only, it's not just important from like and how do I improve this point of view, it's also important to like understand the risk in terms of like running it in this way versus running it like traditionally the way that we would do it otherwise. Because in some cases, if we, for example, are like recording health notes like for people like in a hospital, if we like forget to record like a really important diagnostic that exists like for a particular patient, and like the doctor never sees it because it never makes it into the patient notes, that could be disastrous for like some individuals. And so you have to also be kind of looking at this in terms of the context in which like we're using the LLMs. What is the use case here? What are the checks and guardrails? Like everything in terms of like, is this viable for this particular use case? But still, like you could get a lot of gain out of this because it's still cheaper than maybe having a person do it, and it may still be more reliable than having a person do it. It's just a matter of like, now that we understand that it is reliable, how can we like push that reliability to the limit? How can we try to get this to work as best as possible?
Yeah.
So yeah, I think it might be, it's like 2 hours almost since we got started. I think if we don't have any more questions, I might hand it off to Asif, who's
Yeshila, excellent presentation, and thank you for putting in the effort to organize it and bring it together. It really was wonderful, very educational, and very engaging. Lots of interactions and lots of discussions. For those of you who were asking for the slide deck, Yeshila has shared the link to the Google Doc. At the same time, I've added her link to our Discord server, weekly paper reading channel. If you are not part of our Discord server, I'll again invite you to join our Discord server, please. Andrew's question, is saving the chat disabled in this Zoom? I don't know. I don't know how to find that out, whether it's enabled or disabled. But in any case, the YouTube, because it's being streamed on YouTube, you can see all the chats there. At least I did not explicitly disable the chat with that. So once again, Yeshila, thanks a lot. This was again really a wonderful, wonderful presentation, and it must have taken a lot of effort to put it together. Really a vote of thanks from all of us. Any closing thoughts, folks, before we stop recording?
No, as you said, it was a great and a wonderful presentation, Yeshila. Very, very good. It's a lot of information presented in a nice way. Thank you.
Yeah, thank you for having me. And yeah, Mike asked, can we do a second part for the implementation? I would love to. And if Asif wants me to come back in the next couple of weeks, we can do that as well.
Yeah, absolutely.
Oh, absolutely, absolutely.
Yeah, awesome.
We'll give you, Yeshila, 1 week. There's in between. Adarsh will be presenting next week, but the week after that, please do come by and do part 2 of your presentation on agents.
Yeah, sounds good to me. Thanks. And
Fantastic.
excited.
Loved it. There's a lot to follow, but you laid out the framework for us to all chase, and piqued all of our interest in it.
Yes. And folks, if it has piqued your interest in AI agents and how they work, and especially agentic reasoning and multi-agent collaboration, please do consider registering for our AI agents course, which is starting mid-August. And it's for Thursday evening, so the day after the paper reading, typically. So Thursday evenings, it is 2 evenings a week. I believe it's Thursday and Monday or something to that effect. It's a pretty in-depth course on AI agents, and you're all welcome to register for that.
Just one suggestion, Asif, can we have a separate channel for all the courses so that this question doesn't get asked again and again?
A separate channel. I will put I mean, those channels do exist. We haven't just, those channels are visible only to the people who have registered. But I could do one thing I suppose I could add a public channel where we list all the courses. Great idea.
Exactly. Yeah.
Yeah, let's talk to, would you mind sending a message about this to Patrice?
I will. I did put that little suggestion, but I will flag